Now let's just discuss about how can we design a simple distributed rate limiter given some requirements, functional and non-functional. So to understand at high level, rate limiter I think should be straightforward. So how many requests a client can make within a specific time frame, kind of simple traffic controller for our API. For example, let's say we allow 100 requests per minute from a user. Then post that we just reject excess request with HTTP status code like 4 to 9, too many requests and all. So it really helps us to prevent abuse or and protect our own servers from being overwhelmed by bursts of traffic and ensure fair usage across all users. So that is a standard way of building our own definition, or the definition of rate limiter is. Now that we clear what is rate limiter is, let's just think of this is a rate limiter for our something like whatever the platforms that we have, APIs rate limiter. Okay, so the core requirements that we should first think of is how can we identify the clients so that it is trying to hit our service. So we should be able to identify clients by user ID and IP and API key. So I'll talk about this the instances, how where it can be user ID, IP and API key. And then the other functional requirement is we should be able to limit request based on configurable rules. So meaning that there should not be any code changes needed for adjusting limits, something so that we don't need additional code deployment whenever we wanted to update the rules. So that's the second requirement. Then other thing is that we should need to make sure is we if it is something that requests are exceeded, we return proper error codes like 4 to 9 with proper meaningful rate limit errors, like how many are left, the rate limiting count, and then what is going to be the waiting time. So what is the timestamp for the rate limit gets reset and all everything. So those are the helpful headers that we need to pass it in our response. Then other things which may be good to have is providing analytics and rate limiting data that we are keeping track of. And then of course we need to support storing those rate limiting data for longer time, like for further analytics and all that stuff. So that's the simple the functional requirements. I think maybe we'll try to cover first 3 points. And non-functional is the minimal latency. So whenever there is a rate limiter behind a particular service, the response that user should expect is always less than 10 milliseconds. So that's very minimal criteria for better user experience. So that's something we should meet. And then other is availability should be considered higher priority than consistency. So eventual consistency is okay, as slight delays in limit enforcement across nodes are acceptable. So we need to make sure that it's always up, then the data is not synchronized across all nodes. So that's something that trade-off. And the scale wise, we should be able to handle 1 million requests per second. That's hitting maybe let's say 100 million daily active users platform that we have. Okay, so these are like rough highly functional and non-functional points that we should be able to meet these things. Okay, so looking at this, if you see the main core entities, just at a high level we should have it is like we have clients, so the clients entity, and then we have a rules entity that we need to have, and then other is a request that will be getting as an incoming API request. So those are the core entities, so rules, clients and requests. So here rules are simple, let's say it specifies maybe like I can say authenticated users get 1000 requests per hour, and there is like search API only allows 10 requests per minute per IP, or premium users get 10 times more than normal, something like that, or our global service has a limit of this numbers of requests per second, something low, like those examples is something that we'll try to store in this rule section. The other thing is clients. So that is like entities that we are trying to rate limit. So it can be identified by user ID. Basically user ID is something that authenticated users, and normal like anonymous users, or if it's something public APIs, we will just try to identify by IP. And if it's a developer API, we try to identify by API key. Okay, so yeah, that's the second core entity. The third entity is a request. So this is a simple incoming API request that needs to be evaluated. So it might carry something like, you know, client identity or endpoint that you're trying to access, and then timestamp, which really helps us to identify which rules to apply and how to track usage and all that stuff. So the flow is going to look like this. Request is going to arrive, and we try to identify the client from this request, and then this will try to look up the rules, which will try to help us check current usage against those rules, and accordingly decide whether to allow that request or deny the request. So this is like simple core entities that we have. Fine. And system interface, since this is a more of infrastructure component, there is not going to be much of an API services that will be exposing. So it's a simple straightforward, assuming we have a simple straight interface is request allowed. We pass in the client ID and the rule ID, and you just needs to do some magic or logic or whatever it has, and give us just let us know, is it a pass or fail. So accordingly we can let it to talk to respective service, and then how many are remaining, and what is the reset time. So these are the things that we expect, at least the minimal the return response from our is request allowed. Yeah, now that we are clear, at least we have will be getting from this system interface. Let's now try to discuss one point at a time from our functional requirements. First thing is identifying clients by user ID, IP, or API key. So that's, we know that we need to identify by these things. But the question is, where are we going to identify exactly, and how are we going to achieve that? So I think this should be a simple. So basically, in our architecture, where is it something that we need to place our rate limiter is something. This is more of a question thing. If there is three ways. So one is I can try to directly put in process, meaning I'll just add a rate limiter right in front of my respective microservices. So it might look something like this. So I have, let's say I assume a simple client is hitting our gateway, and we have some, let's say, microservice 1, 2, 3 or whatever n. So I'm just trying to add rate limiter in front of my microservices, and then it will just it will just have in memory local counters and updates them and decides whether to allow or reject the request. This is extremely fast because everything happens in memory and no network calls, no external dependencies. But the downside is this here. Each server will have its own rate limitings built directly into its application code. Sorry, this is not downside. The points that I just explained to you. The downside is this. So now this service will only know about its own traffic and not about the global picture, meaning it will not have an idea of how many requests were routed to microservice 2 and microservice 1 and all. So each server will only know about its own traffic. So there is a chance that user will get more than what the limit that we have configured. And this is actually ideal only when we have one server, because we don't need to worry about global picture. So this is something that is not considered given that ours is going to be distributed system. Okay, so the other thing is maintaining our own dedicated service. So here what happens is rate limiter itself becomes its own microservice. Basically here it's the design. So this basically tries to sit between our clients and then the microservice. So here when a request arrives at an application server, the server first makes an API call to rate limiting service, and then gets that boolean passes and other the things that it needs, and depending upon that it will just allow it to go to that respective service or deny with the 429. So it really, so this is something like it gives us more flexibility because we'll have more rich context information. Here we can control more, because we'll have an access to application code. We can really add a very complex logic for rate limiting, like user subscription tier and account status, and can really handle complex logic. Let's say we try to give more request during new year time or year end time and all, something that we can really get all of that context inside our application layer and pass it accordingly. And it really helps us maintain now only strict limits that we have, because it's a global counter, and only on request minute per minute, whatever the rules that we have configured. The downside is basically it adds additional latency. Now every request that we are trying to send to our gateway to respective service, it needs to route back round trip from our Redis to service. So for every new request now, it needs additional round trip from Redis. So this is something that is going to add latency. And also now we have introduced new service, which is again a single point of failure FOMO that we might have. And also operational overhead. So what if it fails? Like, should we allow the request to go through our service, or should we deny? So that is something again we need to think of and add those strategies and all that stuff if we choose this the dedicated service. The other way is we can place our rate limiter in our gateway or load balancer. This is a more ideal approach, and that's actually preferred in most of the applications. So basically the rate limiter, whatever we have, it tries to run at the edge of our system itself, integrated mainly into our load balancer or API gateway. So now every incoming request, it will first hit this rate limiter before it reaches any of our services which are behind the gateway. And it tries to check the IP address, user authentication headers, API keys, and all those things. So here, a load balancer API gateway. And the downside is we'll not have more context info like we had when we maintain dedicated service. We only have information of whatever the HTTP request that we are getting. So that thing. And the other thing that we need to think of is, where are we going to store this rate limiting state? Is it something external again, Redis and all? I think that is something that we need to think of. And how are we going to identify clients? So for authenticated users, we can use something like authorization header in the request, like user ID. For public APIs or anonymous users, we can use IP address, maybe user agent or X forward for key in our request, HTTP request. For developer APIs, we can just look for X API key. So this is something that we can straight away use this to identify different clients that are hitting our services and all. This is a simple way of how do we identify clients and where do we place the rate limiter. That's our first functional requirement. And then the coming down to a second one, how are we going to limit requests based on configurable rules? So basically, how are we going to handle this? Which algorithms will we be using it and all? This is something, the more detailed discussion or important discussion point in this rate limiting algorithms, wherever we are trying to discuss about. The first thing is there is a fixed window counter, the algo. So basically, what is this simple? So like I think this picture itself should convey you. We try to divide this time into fixed windows. So here, let's say this is 1 minute window, and this is 1 minute window, and this is 1 minute window. And let's say we have a limit of 3 requests per minute, and here we have only 2 requests per client or whatever ID that we have. Here we have 2 requests, so we are passing it through and it is successful. And here now we have 4 requests, but our limit is 3, so only 3 is successful and other 1 is rejected. So this is what is simple as that, and above figure. Then it should wait for a new time window to make a new request, and then we should be able to let them go through our service. That is a simple fixed time window, and it's very simple to implement as well, because all we need to keep track of here is the client ID, can be user ID, API key, or the user agent, whatever we just discussed in previous point. And then we need to keep track of window start time and the counter. So basically for this client ID, for this window start time, what's the counter? So if it is below the threshold that we have, we'll just let it pass through, or else we'll just reject that. So the problem here is the boundary effects. And so basically, let's say here I'm at the 59th second, and user is trying to make 3 requests, and again at 1 minute is trying to make 3 requests. So here we have now, ideally in 2 seconds itself 2 requests, 6 requests, which is something like adding more overload. And then rest of the seconds, like 59 seconds, there's not going to be any way for user to request. So that is something, boundary effect and starvation, that we need to address. So this is something that's not scalable and it's not preferable. So that's one approach we can think of. The other thing is sliding window log. The sliding window log is also like, it's what it does is basically it keeps log of individual request timestamp, like for each user. So what happens is when new request arrives, we will try to remove all of the timestamps older than 1 minute ago, and check now if the count of all the log within that window is in bounds or not. So yeah, that is something. Since we are maintaining a timestamp for each user for every request, so we can just check for previous minutes window. So for example, in the above image, so here they assume this is 1 minute window, and we have 8 requests rolling per minute limit. And since we have for this 3, and here so there are more than 8. So the things that here we are just denying, and rest we are allowing, and all in the previous log that we have maintained request timestamps. So the downside of this is since we are trying to maintain every request timestamp for each user, there's going to be a lot of memory usage, because we need to keep track of all of that. And also the computation overhead for calculating all of the counter use going through the logs of that 1 minute window is also going to add additional computational expensive task for us, because we need to scan through all logs for count check. So this is something the downside. So to mitigate both of the challenges that we saw in fixing window counter and sliding window log, then hybrid approach is going to be a sliding window counter. So sliding window counter is simply, what happens is basically this is a sliding window plus fixed window. So here what we do now, instead of maintaining logs or the timestamp related count, we will just have 2 counters variables, previous window count and current window count. So what happens when request arrives, we estimate how many requests the user should have made in that true sliding window by weighing the previous and current windows based on how far is into our current window. I think maybe that might be something confusing. So here there is a simple example. Let's say we are 30% into our current minute, that is 0.3 thing. Then this 70% of the previous window is something that we need to consider, because it overlaps with our 1 minute time window with 60 seconds, right? So that plus the 100% of our current window count is what is going to be the request that counter that we need to maintain to check the if it request has exceeded that count or not. Okay, so this is a sliding window counter that we can think of to address this. How can we limit based on configurable rules? And the other the popular way is token bucket. So the token bucket is think like each client having a bucket that can hold maybe number of tokens. It can be burst capacity. Burst capacity is nothing but throttle. Let's say it can handle 100 requests per minute. So that's going to be initial capacity of a token. So like tokens to the bucket, which is like refilled rate to the bucket, are added at a steady rate, which is can be like 1 token per second, or whatever we configure. So whenever there are no tokens available in the bucket, the request is rejected. If there is a one, for every request we try to remove one token from this bucket, and if there's no token, we just reject the request. So let's say that initially bucket is holding 100 requests thing, and refill is at let's say maybe 10 tokens per minute, at like maybe steady rate of 10 requests per minute. So client can make 100 requests immediately, because initial burst bucket size is 100 tokens. Then for additional request he should wait for this refill rate. Let's say it fills after for 1 minute 10, then after 1 minute again he can make 10 more a request. So it's something like that. It gets filled in this way, which it really big handles both sustained load and temporary burst. So even if it's hitting 100, because we have bucket size as a throttle value, so it really handles that burst that we have. And what we just need to do is basically simple, the number of tokens that are in a bucket, and then what was the last refill time per that client. So the thing that we need really be very strategic about is choosing the right bucket size. So what should be the actual size so to handle this temporary burst, and what should be the refill rate that tokens are getting filled into a bucket for each client, is something that we should maybe decide based on our experience on that service that we have. So now where do we actually store this? Is it something that we store in Redis? Yes. So the flow is going to be something like this. A request yeah, a request goes to gateway with user ID, let's say ABC. Gateway calls Redis. Maybe this is trying to get multiple field values in a single query, HMGET, and this is the ABC bucket, and we try to get tokens and last refill. And the gateway, what it does, it checks last refill time. So here whatever we got here, let's say it was 30 seconds ago, and assumes refill rate is 1 per second, 1 token per second. Then it needs to update our token count by 30. So it needs to add 30 tokens into a bucket. So because it last updated was 30 seconds and refill rate is 1 per second, and we update add additional 30 to our bucket. So this Redis command might look something like this. Here trying to execute in single atomic operation, multi, then setting this ABC bucket and tokens field, the new token count, maybe 30 in this case, and last refill whatever the current timestamp was, and we automatically set expiry on this key as well, meaning if it's idle for 1 hour, let's say, we will just delete this, expire this and all. So based on this, gateway allows or denies based on the token count that we retrieve from this Redis, and update it accordingly. If it is successful, we just decrement it by 1 and then allow it to access our service. Okay. There is one problem here. While writing there is not an issue, but while reading there is an issue. So let's say that what happens is, if I try to send a request at the same time, both gateways tries to, since we have multiple gateways, they tries to read same initial token count, let's say 30, and they both calculate that they can allow the request, and both update the bucket, and though it is not the right value that it's getting updated for each of the gateway, it could allow even 2 requests when there is only 1 token left in our bucket. So that's something racing condition for reading also needs to be taken care. So to handle that, we need to move entire reading those token and last refill, and also calculating that and updating this everything should happen in single atomic operation, and the best way to achieve is Lua scripting, which is something that we can execute in our on our Redis and make sure that there is no race condition. when we are trying to read, calculate and update, everything happens in single thing. So this way we will try to use this token and make sure that we limit request based on configurable rules, whatever we have here using this token bucket, the simple logic that we just discussed. So that's one one point that we can address. And now we need to reject request when exceeded with the very correct status code of 429 and also helpful headers. So what is the approach here? Meaning when there is exceeded, should we drop them or should we queue them? Should we yeah, that's something. Yeah, this, if it's something like very instantaneous or interactive APIs, the most preferred way is just fail fast, meaning we'll just drop it and we'll try to return something, a response in this way, like 429 status code, too many requests, and what is the rate limit, and remaining is when it's going to reset back, and when can he retry after kind of in 60 seconds and all. So we just provide you a very helpful message so that they can implement their own exponential backup strategies in their own clients and meet the whatever their business logic is all about, something like that. And should we queue them? I think this is something, it's not preferred in most of the design discussions, because it adds more complexity than it solves, it helps in solving. So something that I would avoid it to discuss or anything like that. And now let's go into deep dives and discuss one non-functional point at a time. So first thing is we need to handle 1 million requests per second. So how is it that we can handle this much of a traffic for our system? So let's try to talk the pragmatic numbers of a Redis instance. A typical Redis instance can handle at max 100,000 to 200,000 operations per second. Maybe it can be reading specific key value or writing specific just an operation. Okay, since now our each request, if you see, we prefer token bucket algorithm. We have HMGET, we are trying to retrieve token count and then last refill time, and also we are trying to update that new token and refill time and all stuff. So here HMGET is one operation and HSET is one operation. So basically for every request we are performing two operations. So it falls back to again the limit each Redis instance can handle up to 50,000 to 100,000. So now think we just think, okay fine, let's just spin up more instances and we should be able to handle 1 million requests. Let's say we are assuming at max one Redis instance can handle of 100,000. 10 Redis instances at shard should be able to achieve our 1 million requests per second. But the complexity here is not about spinning up instances. It's like partitioning the data so that each request knows which Redis instance to talk to, and it will know, so that it will have right counter of how many requests are left in that time window or stuff. So how can we achieve is something which is very crucial here to make sure that the request goes to right Redis instance. So the thing that we can think of is or a consistent hashing is something that we can use it here. So since we know different clients here, for authenticated users we know we were using user ID, so we try to hash the user ID and whatever the value that we get, and then we route that request accordingly to that hashed value of that Redis instance. So it will know now which Redis instance to talk to every time, because hash value of that user ID is going to be consistent. It will hit the same Redis instance. Same for public APIs. I will try to hash based on IP address and it will give me some value which will be always the same, and it will talk to same Redis instance. Same for API keys. So this way what happens is I will try to have this consensus, this consistent hashing, and then make sure that it's Redis right instance. So it keeps track of different set of clients or users or buckets and gets bucket data, and then if it is meeting that, it will pass through it, or else it will just reject it. So this way I can with the 10 Redis shards, we mostly in production real time, it's something that we doesn't really take a job of handling all separate instances for ourselves. we just delegate everything to Redis cluster, which really helps us handling this hashing, the thing that we routing and all, everything that needs to be sent will be handled by Redis cluster. So each will handle 100k requests per second and should be able to 10 Redis shard should be able to achieve our requirement of 1 million requests per second. So that's the simple calculation of how can we say hit our 1 million requests. The more the critical point here is partitioning Redis so that each request knows which Redis instance to talk to. So that's one thing that we should really keep in mind, how we can achieve that. And the other requirement is how do we ensure high availability and fault tolerance is something like what if the Redis that we are trying to keep all our counters, last refill time and all these stuff that we need to pick whether to allow it to service or not. If Redis shard goes on, what is it that we will be thinking of? What can we do? So there are two things which is good depending upon the situation or the requirements scenario that we are in. Fail closed is what it is. Basically, I just reject all requests that is coming in with 50 like services unavailable or not available. So I'll just not let it go through my application service. So and then this is a fail closed. Okay, and fail open. Here is basically what I do. I'll just try to allow all requests to proceed as if my rate limiter is disabled or is absent, and try allow the user to hit my application service and get whatever they want. So basically what happens here is if burst request flow in which made our Redis shard go down, can also result in cascading failures, meaning can lead to more load on our the servers, meaning downstreaming all of the traffic to our servers and bringing the whole system itself down. It's something that really not preferable because it brings our whole system down, and it's something that is not expected in real scenarios. So fail closed is something that it's better way to choose, and also there can be we can choose master replica. So what we do is basically we'll try to, for each Redis shard, we'll try to maintain a read replicas of that Redis instances of, maybe we'll do asynchronous replication to that read replicas, and whenever this goes down particular Redis instance, this comes and takes it over. So this basically will be handled by mostly Redis cluster, which they have failover strategies and all that stuff, which it will be taking care of. That's something we can handle. Make sure that high availability is there with read replicas, and also try to follow this so that we don't lead or to cascading failures of old system fault tolerance and all. So this way we can think of and handle that. Now let's talk about how can we minimize latency overhead. So that's something very important whenever a user is trying to access a specific services. So there's a concept of connection pooling. So instead of trying to establish new TCP connection to Redis for every the rate limit check that we are getting, we can maintain a pool of persistent connections. So this, what it really helps us is eliminates the TCP handshake overhead, maybe which really might take around 20 to 50 milliseconds depending upon network distance, and allows connections to be reused across multiple requests. So this connection pooling really helps us to persist these connections, and so that every time we don't need TCP connections. This way, this is one strategy to avoid or to minimize latency overhead. And the thing, but only thing is we just need to tune the pool size based on our request volume that it is hitting our API gateway and the services, and also the Redis response time. So that's one thing. And another thing is simple, anywhere we talk about latency, geographic distribution. So we try to deploy a rate limiting infrastructure close to users, API gateways and Redis cluster in multiple regions. Let's say user in London talking to Redis instance in maybe, let's say, Virginia and other places in US. we'll see much higher latency than talking to the one in the same region, right? So that trade-off is something like, we can choose for quicker response times and less trying to minimize latency. Yeah, I think between regions eventual consistency should be acceptable for a lower latency trade-off. Yeah, that this might be, I think these are the two things that we can think of when we discuss on minimizing latency and all that stuff. All right, the next point is, how do we handle hotkeys? Hotkeys is nothing but viral content. Uh, we need to know what are the techniques that we will help in scaling this hotkeys while content. So approaches, let's just brainstorm quickly. There are like, need different strategies here. So in this case of rate limiting, there'll be actually, it can also come from legitimate volume clients. So this is the scenario that I'm talking about. It can be like analytics systems or data pipelines, or maybe something apps with aggressive refresh patterns. So to mitigate that, what we can do is client side rate limiting. So we can really encourage the clients to implement their own rate limiting for smooth functioning or smooth traffic. This really prevents accidental creating hot shots, and while really helping us to reduce server load. And to be in practical, let's say we have OpenAI or other SDKs that we have, they really will have their own built-in client rate limiting logic that respects the server response headers that we are trying to send using the logic that we have created. So that's something that it can help mitigate this high volume clients. And the other thing is, we can allow clients to request batching multiple operations into single request, so that they can reduce number of reads that they are trying to hit our services. Then other thing is, introduce premium tiers. We'll try to offer higher rates for powerful users who need them, potentially with dedicated infrastructure. So these are like three ways maybe we can try to mitigate this high volume clients. The other thing is, let's say we have abusive traffic. There's no straight away we'll just block it. Automatic blocking, let's say that, for example, that specific client had hit the rate limits, like let's say 10 times in the last specific minute, then I'm straight away temporarily blocking its IP or API key or user ID by adding them to a block list. So this can be kept somewhere in our Redis shards and only checked in case of cache misses and all. So this way we can, depending upon like that conditions, we can just block them. And another thing is, we can go for DDoS protection, maybe using Cloudflare or AWS Shield, which can detect and block malicious traffic even before reaching our rate limiter. So this is the two approaches that we can handle this viral content or hotkeys that we have. And the last point in our non-functional is dynamic rule configuration. So far we have discussed the rating rules are static and all that stuff. But like I said, production systems really need flexibility to change without having for them to deploy their code base. So how can we do this is something straight way. There is two ways: pole based and pull based. So pole based is basically, what I do is, let's say it's a simple strategy. I try to store rule configuration in some my rules table. It can be simple as like, I have columns like client type, endpoint, and request per minute, etc., and all that stuff. So I try to store those details in my rules configuration database, and the API gateways where our rate limiter is actually sitting, it will try to periodically poll for my database for configuration changes if there are any, and it will try to pull the latest rows from that DB, and if it's something that is changed, it will just update the logic accordingly and then implement that configurable rules. But the downside is, there will always going to be update delay. So let's say that the change that I made is 30 seconds ago, and we are trying to pull every 2 minutes or 30 seconds. So there will be delay of whatever the time that I have dated and then the time it is pulling it. So there is some delay. The other, to mitigate that delay, there is a push based configuration approach. Here there are systems exclusively designed for handling this distributed configuration management. For example, Zookeeper, etcd, or we can even think about Redis PubSub. So what this does is basically this whenever there is a change in a rules, it notifies all of our API gateways that there is some change, and then it updates accordingly in that respective API gateways rules sections and all. So this configuration service, whatever we are talking about, etcd or Zookeeper, it will immediately notify all our API gateways and with updated rules within seconds and all. So this way, something that we can really prefer poll based or push based. The challenges here is basically again more complexity, and we need to handle all of the fallback uh, mechanism and also connection failures, like if how do we ensure like there is a partial failure, meaning only few API gateways receive updated rules and not others, and what do we do in those cases or something like that is something that needs to be taken care of. And so this is not mostly preferred unless it is very sensitive, like dealing with security incidents or HFTs and high frequency trading scenarios that we have. Is something that is this is ultimately preferred, or else mostly this poll based configuration is something it can be adopted mostly. Yeah, so at a high level, this is how we can think of when we are talking about designing a simple rate limiting system.